In this example, we want to find the domain and range of this given function and then graph it. So it's useful to figure out what type of function this is. If you notice, we have a polynomial over a polynomial, and so that's going to be what we call a rational function. So what's the domain of this rational function? So remember, domain are all the values that I can input into the function. So where am I going to have a problem here? The rational function, you're going to have a problem wherever the denominator is equal to 0, because you can't divide by 0. So let's see the problem areas first. Basically, I want to solve this quadratic equation. So there are two different ways you can do it. Go ahead and put this on pause. See if you can solve this. Okay, one of the easiest ways to solve a quadratic is to try and factor. So I want to try to find two numbers that multiply together to give me -10, that add to give me 3. So that's going to be 5 and -2. So I'm going to have x plus 5 times x minus 2 is equal to 0. So this is either going to be 0 when x plus 5 is 0, which means that x is equal to -5. Or it'll be 0 when x minus 2 is 0, which means that x is going to be equal to 2. Alright, so those are both numbers that are going to cause my denominator to be equal to 0. So those numbers cannot be in my domain. So that tells me that my domain is going to be all real numbers except -5 and 2. And then I want to go back. I didn't mention the other way you could solve this. If you didn't factor, you could use the quadratic formula instead. Okay, so before we find the range, let's actually go on and graph this function. I find it's a little bit easier with rational functions to use the graph itself to find the range. Okay, so we'll move on to a new page to try and do the graphing. Before I show you how to do it, though, I want you to put it on pause and see if you can come up with the graph of what this function is going to look like based on what we've done in class. For the rational function, it's always great to try and see if you can factor and simplify it all. And so we know from our factoring on the previous page that the denominator can be rewritten as this. And so it means that we are going to be able to simplify, so I can actually cancel these factors here as long as x is not equal to -5. So this tells me that I'm going to have, in my numerator I'd have a 1 left over x minus 2. So this tells me my original function here is going to look the same as this simplified function here as long as x is not equal to -5. Okay, and when x is equal to -5, we're going to have a hole in the graph at that point. So this is a new way of writing the same function that we've been working with. And this is what we'd like to graph. So now you can try and break this graph 1 over x minus 2. You can try to see, does this look like any graph that we've already looked at in class? And so recall from class, we've looked at the graph of y is equal to 1 over x. So again, put it on pause, see if you can remember what that graph looked like, and then use that graph to come up with 1 over x minus 2. Okay, so 1 over x, that's not going to be defined when x is equal to 0. And let's look at what's happening. As we come in to 0 from the right, I'll have 1 divided by a really tiny positive number. That's just going to shoot up to positive infinity the closer I get to 0. Similarly, as I come from the left, this is going to shoot down to negative infinity. So I'm going to have a vertical asymptote when x is 0. Now when x gets huge, 1 divided by a huge number, well, that's going to get smaller and smaller and get closer and closer to 0. And then same thing when I have 1 over, and I'm going in the negative x direction, 1 over x, when x is negative, is also going to get closer and closer to 0. So we're going to have a horizontal asymptote when y is 0. Okay, so if we just want to graph 1 over x minus 2, we can take this graph of 1 over x and we notice that's going to be a shift to the right. So now my vertical asymptote is going to happen here when x is equal to 2. And other than that, the function's going to look the same, just shift it over. This is just the graph of 1 over x minus 2. We actually want to graph our original function, so the original function is going to have a hole when x is equal to negative 5. So actually, let me extend this graph even further. So we go out to negative 5. And one of the things I'd always like you to label on your graphs are any x or y intercepts. So notice we have a y-intercept right here. That's going to happen when x is 0. If you plug in 0 for x to this function, we're going to get negative 1/2. So this is going to be negative 1/2 here that you want to label. All right, now we want to now graph our original function, so we have a hole at negative 5. So here at negative 5, I'm going to erase a little space of the graph and leave a hole. And it's even more useful if you can label the y value where the hole would occur. So notice, if you come back to this function, if x was allowed to be negative 5, we plug in negative 5 to this, we're going to get y is equal to negative 1/7. So that means the y value, it's right about here, it's hard to see, that's in line with the hole, that's going to have a value of negative 1/7. Okay, I know that's really hard to see where I'm writing it, but just to give you an idea of the types of things you'd want to label. Negative 1/7 right there. Okay, and so this is going to be our final graph right here of our original function. And actually, just to be complete, you'd also want to have, let's label something on this part of the y-axis, just so you can see what we're counting by here. Okay, so we have everything labeled, and there's our graph. So let's go back now. Now that you have the graph, it's a little bit easier to finish up and find what the range is. So remember, the range is going to be the output of my function. So what you can do on the graph is scan your pencil along the y-axis. And you want to find all the values along the y-axis where the function is mapped to. So I start down at the bottom of the y-axis, down here near negative 3, and I say, are there any values in my domain that map to negative 3? Yep, you can see there's part of my graph there. And I keep moving up, and I say, okay, are there values in my domain that are mapping to each of these y values as I move up? And I stop as soon as there's a hole, or as soon as there's a y value that is not mapped to by this function. And so that happens right here when y is equal to negative 1/7. So y cannot be equal to negative 1/7, and that's because x is never negative 5. There's no value that I can input into the function that will give me negative 1/7 as the output. I'll continue up along the graph, and I stop the next time I hit a y value that's not in my range. And the next time that happens is when y is equal to 0. You can see this function never crosses the the x-axis, and so that means that y is never going to be 0 in my range. Then we continue up till we get towards the top of the y-axis, and you can look and find values in the domain that map to all the rest of the values along the y-axis up there. So the only values that are not in my range are negative 1/7 and 0. All other real numbers are in my range. And that's it.